Hey everybody, and welcome back to this channel, or if it's your first time here, welcome to this channel. I'm David Townsend. This is the Net Academy, where we are learning networks together. And on the previous video that I put onto my channel, what I went through is what is BGP, or Border Gateway Protocol? Why is it here? Why is it needed? How does it make the internet work? And what are the different flavors of BGP, such as eBGP for exterior border gateway protocol, i.e. between different autonomous systems, and then there's iBGP, or interior border gateway protocol, for communication as such in the same autonomous system, and of course a basic Junos config between two MX routers between two different autonomous systems. What we're going to go through in this video, though, is stepping away from the basics just a little bit. We're going to go into what is iBGP, what is its rule set, and that's very important because iBGP is quite a bit different to eBGP. eBGP, as soon as you define who you want to peer to, i.e. the neighbor address, and what is that peer autonomous system that you want to peer to, generally it just works. Whereas iBGP, we have this particular rule set which says, well, if you're communicating to this type of router or to this type of node, whatever it may be, I may or may not advertise prefixes and learn networks to that peer, depending on who I actually am, and so on and so forth. So we're going to go through what is this rule set, and also we're going to go through what is this AS path self that is absolutely essential to getting that end-to-end connectivity to work, i.e. to ping from one router inside an autonomous system to ping to an end destination, wherever that may be, but outside of that router's autonomous system itself. So quite a bit of information to go through, so let's just jump straight onto the lab and let's get going. And here's the lab that we're going to be using for this video. So it's the same lab as we used on the previous video, and that we're going to be using in future videos as well. And on the previous video, what we did is we configured eBGP between these two routers here, i.e. between autonomous system, you can't see it, but this is autonomous system 65100 over to ISP1, i.e. in ASN1, as well as eBGP down here as well. Since then, I've configured eBGP really between all the different autonomous systems, so they're all connected together. Now, the purpose of this video isn't to go into eBGP. We've already done that in terms of a basic configuration. The purpose of this video is to go through iBGP. Now, to do iBGP, the I is of course standing for internal. So we're going to configure internal to ASN1. i.e. we're going to configure all these routers to be or to have peering to one another. And there's a reason why you want to have what's called a full mesh connectivity. We'll come on to that in just a few minutes time. First though, what's important to remember from the previous video is that the eBGP peering was built using the interface's IP address. So we used this IP address here and this IP address here to actually build that eBGP peering. Now with iBGP, actually I should do a small I. With iBGP, we don't use the interface's IP address. What we do actually use is the loopback 0 unit X IP address. So even though in the Junos world there is only one loopback, you could have X amount of sub interfaces or units, each one with their own IP address. Now the way that these loopbacks are actually learned is via an IGP. So that would be OSPF, that would be ISIS. In this network here, I will show it just briefly. I've got intermediate system to intermediate system running throughout this entire network here. So all the loopback zeros, so we've got .1 here, we've got .2 here, we've got .3 here, and .4 here, are all being advertised via ISIS. So really IGP, ISIS, is providing what's known as the underlay connectivity, and then we're using iBGP to configure what's known as the overlay connectivity. So the underlay is really just providing that, we wouldn't call it the physical connectivity, but just the connectivity between the interfaces and the loopback addressing to advertise the loopback addressing into the underlay. And then the iBGP, the overlay, is actually peering based on those loopback addresses, which is learned via the underlay in the first place. So that's one of the subtle differences between eBGP and iBGP. Now, the objective of this video for this session really is on router R5 here. I want to create a static route of 5.5.5.5/32. So it's going to simulate that of a host, and I want to advertise that via a policy statement. I'm just going to say PS for short. I'm going to advertise that into eBGP. Now we know the peering is built from here to here. When this advertisement is coming up to router R1 here, we then need to investigate into what actually happens. Now, coming on to the rule set of iBGP, there is a particular rule set that you need to be aware of, and that is when this learned network comes up, and that will again be the 5.5.5.5/32, even with the policy statement configured, if we've got the adjacency built from R1 to routers R2 and R3 respectively, routers R2 and R3, if they've got their adjacency built and established to router R4, they will not send those updates down to router R4. This is one of the rule sets, is that when it comes to iBGP and the learned routes, an eBGP can forward onto an iBGP, an iBGP speaking router can forward onto an eBGP. However, you will not see iBGP routers forwarding on a learned route to other iBGP speaking routers. And that is why I said we need that full mesh connectivity. It's really one of the limitations of iBGP. It's a scaling limitation where not only do we need to build the adjacency from R1 to R2 and R1 down to R3, we also need to build the adjacency from R1 over to R4. And again, that comes back to that loopback 0 being advertised via that interior gateway protocol. So R1 knows of R4's loopback address and it can get to it via either R2 or down to R3. The screen is getting very busy, so I'm just going to tidy it up. But that is the rule set of iBGP, is that we need a full mesh connectivity to allow that learned network of 5.5.5.5/32. So when it comes up, it is advertised over to R2, to R4 and R3. If we didn't have a full mesh, that learned route via that policy statement on R1, it would get to routers R2 and R3, but then they wouldn't do anything with it, because they'll know that router R4 is another iBGP speaking router, and my rule set is not to forward it on. It's a loop prevention mechanism basically. Hence R1 also has to have that adjacency to router R4. So let's actually jump onto these routers now in autonomous system number 1 and actually start configuring iBGP. So I'm on the command line of router R1, and if I just do a quick show route, you can actually see I've learned of R1's loopback address. So this is the loopback address basically of 200.10.1.1, so .1 meaning R1. This is directly by R2.2, R3.3 and R4 here are all learned via ISIS. So ISIS is providing that underlay connectivity. But let's actually go into configure mode and let's configure iBGP. So let's do edit protocols BGP, do a quick show, and you can see we do not have anything for iBGP. Now just like eBGP, again, if you don't know how to configure eBGP, check out the video down in the description box. But what we still need is a group. So let's do set group, and I'm going to call this internal to AS1 for autonomous system number 1. So I've got my group here, and I need to say this is type internal. Also, I need to define my local address. Now this is the loopback 0 address. So 200.10.1.1, that is the loopback 0.0 address. I'll show it in just a second. That is configured on router R1. Also, I need to define the loopback addresses that I want to peer to. And if I just scroll back up, you can actually see you've got R2's loopback address here, R3's loopback address here, and R4's loopback address just here. So I need to define those loopback addresses. So there's R2, R3, R4, And now if I do a quick show, you can actually see how is it configured. So we've got type internal, so it's iBGP using my local address, and I want to peer to these neighbors internally. And if I just do a quick top show, interfaces loopback 0.0, unit 0, you can actually see here's the loopback address here. So 200.10.1.1, and it's actually referenced here. So that's important because, as I said, the loopback 0 can have many units, or in the Cisco world called sub interface. It's exactly the same thing. So let's just do a commit and quit, and now I'm going to go on to route R2 and do exactly the same thing. So just quickly, let's go into edit protocols BGP, just do show, and there's nothing there, so let's do set group internal to AS1, type is internal, local address is 200.10.1.2, so that's R2's loopback address. And I want to peer to the neighbor of 200.10.1.1.3 for R3, .4 for R4. Let's do commit and quit. And on route to R3, let's do edit protocols BGP. Let's do show, nothing there, so let's do set group internal AS1, type internal, local address is 200.10.1.3 for R3, and I want to peer to neighbor 200.10.1.1, that's R1.R2 and R4, and let's commit and quit. And finally on route to R4, let's do edit again, let's do edit protocols BGP. That should be nothing there. I've got my external as well to go over to enterprise B, but let's do set group internal AS1, autonomous system number 1. This is internal. My local address is 200.10.1.4 for R4, and I want to peer to neighbor 200.10.1.1 for R1, .2 for R2, .3 for R3. Let's commit and quit. And now they're all connected, so every router has now got a peering to one another. iBGP is working their established connectivity within the same autonomous system number. Now, as I said, what we want to do is we want to build a static route of 5.5.5.5/32 on router R5, and we want to export that via a policy statement from R5 into eBGP so that router R1 actually sees it. So I'm on router R5, and let's actually start just configuring this. So if I just do a quick show on the BGP protocol, you can obviously see we've only got the external AS1, so the external BGP, eBGP. So let's just go to the top and let's define that policy statement. But first we need to define the static route. So I'm going to say set routing options static route, and we want to do 5.5.5.5/32. Now I'm going to define a next hop of reject. What that means is that when I ping this IP address, because it's a /32, when I ping this IP address, I'm going to get an ICMP response, even though it really doesn't exist. And in the routing table of R5, it's just going to discard really these packets. It's still going to send an ICMP response. So basically I know that the routing is working, that the connectivity is there. So reject, and that's my static route obviously configured. Now I need to define the policy statement. So let's do edit policy options, policy statement, and I'm just going to say advertise 5, just for example for 5.5.5.5, just keeping it short. Let's do set term 1 from protocol static route filter 5.5.5.5/32 exactly. And now I want to say set term 1 then accept. Let's do a quick show on that, and you can actually see there I've said, well, from protocol static, if it matches 5.5.5.5/32 exactly, then I want to accept this. But we now need to export that into BGP. So I'm going to go to the top and go into edit protocols BGP. If you don't know the basic commands on Junos, here's a link to help you navigate around and know what edit is and top is, etc. There's quite a few commands, so check out that video. But let's go to the top and then move in within the protocol branch within the BGP. So as I said, we've got our external BGP, and I want to now set group external export. Now by question mark, you can actually see there's a bit of a ghost there, advertise 5. I want to export that into BGP itself. So if I now do show, I'm now exporting that policy statement I configured. If I just scroll up, which is just here, I'm now exporting that into BGP itself. So if I do commit and quit on here, and with that now successfully committed, this makes sure we are actually advertising that static route. So let's do show route advertised protocol BGP, and now I need to define, if I hit question mark, the neighbor. Now the neighbor in eBGP is the remote end, either the remote end of that link, its IP address. So 170.10.20.2. That is this interface here and the IP address here, because eBGP uses the interface's IP address to build the adjacency. So if I hit this, you can now see R5 is advertising 5.5.5.5/32 over to this particular neighbor via BGP, and it is advertised automatically its next hop of self. That's great, 5.5.5.5. And you can see it can, because of that reject command I've done on R5, I'm getting that response. Now, the next question is, on router R1, are we actually seeing this? So if I do run show route received protocol via BGP from the neighbor, because I still need to define the peer or the neighbor, same thing really. So now I need to define the IP address of the R1 interface, which is 170.10.20.1, and you can actually see that is coming over. So I've received it 5.5.5.5, next hop of 170.10.20.1, and it's going to this autonomous system 6500, which is up here. Can R2 ping 5.5.5.5? So let's do ping 5.5.5.5, and absolutely not, because it hasn't got a route to the host. As I said, we need that policy statement on router R1. So if I actually just do, and just to prove that, if I do run show route advertising protocol to, well, through BGP to 200.10.1.2, because this is an iBGP relationship, you need to define the loopback zeros IP address, not the interface IP address, because eBGP builds peering on interface IP address, iBGP builds peering on the loopback IP address. So that's what we're defining here, and you can see that it is actually advertising it. So 5.5.5.5 has been advertised over to the neighbor 200.10.1.2. So on R2, let's have a look. Let's do show route. Do we have 5.5.5.5 in our network? We do not. There is a reason for this, and let me come into that. So if I just do show route received protocol BGP from the neighbor 200.10.1.1, that is R1's loopback address, we can actually see that there's nothing here, but there is two hidden. So to see those hidden entries, which basically are being discarded, if you write hidden at the end, we can now see that we have got the 5.5.5.5, which has been received from, as we know, from R1. But this is the problem. The problem is right here. The next hop is 170.10.20.1. That is this interface over here. Now that is external to autonomous system number 1. Now the ISIS, the IGP, it's doing a great job of advertising the loopback addressing from these different routers across the autonomous system itself. They're all learning who the loopback addresses are, and of course the interface's IP addresses as well. However, what ISIS is not doing, and even iBGP, is it doesn't know of this link right here. It just doesn't know of its existence. And this is one of the limitations with iBGP. It's not just the scaling and the fact that you need a full mesh, but with eBGP, when that 5.5.5.5 is advertised into autonomous system number 1, the next hop is automatically defined to be that interface's IP address. That's basically what you're seeing here. However, router R1 does not then change that next hop. It doesn't define, well, if you want to get to that 5.5.5.5, then you need to go through me. It doesn't define that at all. And that's actually where, as I said, we need that policy statement configured on R1 to actually change this behavior, because without what is known as next hop self, and all vendors have this, then in this case router R2 is never going to be able to ping that 5.5.5.5 host, that network, because it simply does not know of this external network. So we need to first define that policy statement. So on router R1 it's going to edit policy options. Let's see if there's anything there. There's not. So I need to define a policy statement. So let's do edit policy statement, and I'm just going to call this, I'm just going to call it PS for policy statement, just keeping it short and easy to remember. Now, as always, we need to set a term. So I'm going to say set term 1, then next hop self, and say then accept. If I do a quick show, we can now see we've got a very basic policy statement here, which is saying, well, I just want to configure the next hop to be actually myself. Now, to then configure and to have this policy statement in the BGP protocol, i.e. in iBGP within autonomous system number 1, we need to export this policy statement into BGP. So let's go back to the top and do edit protocols BGP. Let's just have a quick look again. Now what I want to define is I want to export that policy statement just here into our internal iBGP. So let's do set group internal export, hit question mark, and there we go. So if I do a quick show again, you can now see it's configured to export that policy statement I just configured. And let's do a commit on this, and there we go, that's now committed. So if we come over, back over to router R2 now, let's have a look again. So let's run that same command again. So is there anything hidden? There's nothing hidden now. There's a bit of a ghost here. It's a virtual environment, so and yeah, it's not always going to be 100%. But you know, the 5.5.5.5 is no longer hidden. That's a good thing. So now if I just remove the hidden command and just do show route receive protocol from BGP from that R1 loopback interface, we can now see all of the routes which we are receiving via BGP. So I've got 5.5.5.5/32 here. Now I can see the next hop of self. So back on router R2 now, let's run the show route received command from BGP from neighbor. Oh, we don't have to hit the neighbor command, let's just do 200.10.1.1. And here is the 5.5.5/32. Now you can actually see the next hop is 200.10.1.1. So now R2 knows if it wants to get to this destination, it's got to go through R1. So let's try the ping now. Let's try ping 5.5.5.5. Now I'll tell you now, this will not work. As you can see, it is just timing out, and there is a reason to this. So what I've done is I've just done a quick Wireshark on the GIGI 001 interface on router R5. Now I'm just going to run that same ping on router R2 to go over to that 5.5.5.5. So we can now see those pings being populated in the Wireshark. That's more than enough for the explanation purposes. So I'm just going to move it over. So we've got this destination of 5.5.5.5. Now that is correct. R2 is trying to ping that destination, and that is correct because that is configured as a static route on router R5. R1 knows how to get there. R2 knows how to get to R1. We configured that policy statement with that next hop of self within there and exported that into iBGP. So what is the problem? The pings are coming from here to router R1. R1 is forwarding them onto router. I'll just do it there just to be a bit more specific and precise. The R1 is then forwarding those packets, those ICMP pings, over eBGP to router R5. But this is the problem, is the source. If you look here, the source is 192.168.1.2. Now you can't really see it, but that is the GIGI interface right here. That is R2's GIGI interface that is facing router R1. The problem specifically is router R5 has no idea of where this network actually is. And just to prove that, if we actually go onto R5 and do run show route, do we see a 192.168.1.2? We do not. We see our 5.5.5.5. Yeah, we've created that. We've got our external networks. That's the eBGP. Basically, yeah, it's a direct link, but that's what we're using to build the eBGP peering between autonomous systems. And then we've got our internal networks as well. But we don't see at all a 192.168.1.2. We've got 192.168.100s, 100s, 100s, 100s. Well, sorry, these are the loopback interfaces, but you get the point. That is why the ping is getting to R5, and then R5 drops it because it simply does not know who that source is. It's not in the routing table. How can we configure that? And the answer is simply to have a policy statement on router R1 which says for these interfaces on routers R2, R3, and you can't see it, but R4, which would be about down here, I want to export them into eBGP so that R5 learns of those external networks. So when a ping comes through, it knows how it's going to respond to that source. So on router R1 now, I'm in the policy options. So if I just do a quick show, we've got that policy statement that we configured earlier. And in fact, I'm just going to rename this to next hop self, INHS. So if I just do show, that's just going to be a bit more specific and a bit more relatable as to what that policy statement actually means. Now that next hop self policy statement, that's for our iBGP. That's so that router R1 changes that next hop not to be the R5's GIGI001 interface with that IP address there, but to be its own IP address, so that the iBGP routers have the knowledge of where to route those packets to. Now we can't change that for this particular case. We can't change that policy statement. That policy statement of next hop self NHS is being exported into iBGP. So if we were to change that by adding in protocol IS, etc., we could introduce routing loops. We obviously don't want to do that. What we do want to do is define a different policy statement where we're going to take the direct links and the IS learned networks and export them into eBGP. Hence, we need two different policy statements. So let's do edit policy statement, and I'm just going to call this advertise internal, or advint for short. And let's just say set term 1. I'm going to keep it nice and quick. So protocol direct, as well as from IS, and then I'm going to say then accept. Let's do a quick show. I'm happy with that. Looks very straightforward, of course, and I'm just going to do a commit and quit on this. So it's probably worth mentioning at this point, because this is very straightforward, because we've defined direct connections, it's even going to be advertising over, when we define it in a second, it will be advertising over even the loopback 0 interface that's configured on R1. So you'd probably want to change this so that that doesn't happen. You don't want to advertise your loopback interface outside of your autonomous system, of course. But in the meantime, and I don't know why I don't commit and quit, but let's do edit protocols BGP. Let's see what we've got. And again, we need to define the export into the external autonomous system. And if I hit question mark, there's the policy statement I just configured. Let's do show again, and we can see it's now configured here. And now I would do the correct command of commit and quit. And now if I do a show route advertising protocol BGP, and that's going over to the neighbor R5's IP interface. So that's 170.10.20.1, and we can actually now see we're advertising all these networks here. Again, it's advertising everything, even the loopback addresses, because we wasn't very specific in that policy statement. So this is questionable, very questionable, but for this purposes, for this lab, it's okay. We can get away with it. So we're advertising it, but on router R5, do we have those routes which have been learned? So let's do that again, show route, and now you can see it's installed the 192.168.1.0, 1.4, 1.8 and 1.12 networks. So those are the networks which are inside ASN1. Now the ultimate question, can R2 ping 5.5.5.5? So let's try ping 5.5.5.5. And now we are getting a round trip response. So there we go. That was why that wasn't working in the first place. So as you can see with iBGP, there's quite a bit more that you've got to do with eBGP. So let's summarize. We created this static route with a next hop of reject. We built a policy statement which exported that into eBGP. This then came through to router R1. We then had a policy statement which advertised the learned routes down to all these routers and across to router R4, and this also defined the next hop of self. But then we built another policy statement on router R1 to advertise those internal networks into eBGP so that R5 learns of all the networks inside of autonomous system number 1. But as I said at the beginning of this video, what I want to do is actually create pretty much the same again, but another static route over, and it will be a /32 again, over on router R18 here. Hence it's going to be an 18.18.18.18/32 static route. And I want to see, can we ping from router R5 across service provider number 1 all the way across to enterprise B to router R18, because that's really the job of a service provider, is it's providing services, providing connectivity to and from something. So let's actually do that configuration right now. So I'm on router R18 and it's just going to configure mode, and let's just do show routing options, and you can see that nothing really configured there apart from router ID and autonomous system. That's all good, but let's define that static route, routing options, static route, and I said 18.18.18.18/32 with a next hop of reject, and that's that configured. So let's not do the full configuration, let's just do show routing options, and that's now configured there. But just as we did before, we need a policy statement. So let's do edit policy options, policy state, and I'm just going to call it advertise static for obvious reasons. And now let's just say set term 1 from protocol static with route filter of 18.18.18.18/32 exactly, then accept. And now if I do a quick show, we can see that's configured perfectly fine with that. Now we need to then configure and export that into eBGP. So let's go into protocols, BGP, see what we've got configured. We've already got our iBGP peering built successfully in autonomous system 65200, i.e. enterprise B, but we need to export that into eBGP. So let's do set group external export ? There we go, advertise static, and let's run that commit command. And that's now committed successfully. So has R4 actually learned of that route? So if we actually just do show route, and we can now see we've got the 18.18.18/32. That's great. Will we be able to ping that? The answer is yes, we should be able to, because it knows that the next hop is its directly connected interface. So we've got round trip there. But just like we saw before, we need the policy statements on R4, because R2, R3, and even R1 will not be able to ping the 18.18.18.18 because of that next hop self is missing. So let's go into configure mode and let's do edit policy options, policy statement, and I'm going to call this next hop self. And let's do set term 1, then next hop self, then accept. And there you go, we can now see that very quick and easy policy statement. Now, of course, we need to export that into iBGP. So let's do top, edit protocols, edit BGP, show, we've got our external eBGP, we've got an internal BGP. That's where we need to advertise that policy statement into. So let's do set group internal export, hit ? Next hop self, do show, and there we go. And I think I said it before, you could do the export all the way at the group level, which will go towards all the neighbors within that group, or you can do it at a specific neighbor. So if you want all neighbors that you've got the peering built to have the same policy statement applied to them, great. That's great at the group level. However, if you want to do it on a per device, per neighbor, per router level, then you could do that within the neighbor command. So let's now do the commit command, and that's done. But remember, if I go over to router R2, just for example, and do show route, we've got the 18.18.18 network here, but you will not be able to ping it because just as we saw on router R5, R18 is not going to know of all the networks that are inside autonomous system number 1. So we need to export all these networks here directly and learn via ISIS into eBGP from router R4. So we need another policy statement. It's a video all about policy statements today. So let's go to the top, edit policy options, policy statement, and I'm going to call this advertise internal, just as we did on router R1. Let's do set term 1 from protocol direct and ISIS, then accept. Let's have a look, make sure I'm happy with that. Advertise internal term 1 from protocol direct ISIS, then accept. Again, this needs to be a lot more specific. You need to define what you want to filter on, what you want to accept to go through. This is a very blank canvas, but for this lab, for this purpose, as I said before, it's fine. So let's now just go back into edit protocols, BGP, and we need to export that policy statement into eBGP so that the neighbor R18 learns of all these internal networks. And hit the question mark, and I've got my advertise internal policy statement. Hit commit on this, and does R18 know of these external networks? So let's just go to the top and quit out of here. Let's do show root, and you can actually see it's now learned of the 5.5.5.5, which is configured all the way across on router R5. So we know already the ping's going to work, but everything else is absolutely there. Now the question now is, can we get round trip connectivity from R18 to R5? So let's try ping 5.5.5.5, and there we go. Took a split second there, I did wonder, but we have now got round trip visibility. So basically what we're seeing here is that R18 can ping from here up to here, down here, and across to R5, or it might take obviously this route here, and we're then getting that response coming back again via whatever route. And obviously because R18 can ping R1, we know without any specific firewall policies, etc., that R1 is also going to be able to ping R18 in return. And there we go, everybody. That is the end of this video. That was a lot of information to go through. As we now know, iBGP is fundamentally different to eBGP. eBGP basically connects autonomous systems together. They peer using the interface IP addressing. They peer using who's the adjacent autonomous system. And as long as everything's configured correctly, generally it just works. With iBGP though, we've got next hop self and we've got the rule set. The rule set, just in summary, again defines an eBGP router. Learned routes will be forwarded to an iBGP router, but that iBGP router will not forward that learned route to another iBGP router. It's to prevent loops from actually forming, and therefore you need that full mesh connectivity. So on the lab, we connected all those routers in autonomous system number 1 together, so that when those external static routes, which were being exported into eBGP, they were then flooded throughout the whole network, and every router then learned about who is that next hop to actually go to. And of course we've got that next hop self command, as I just said. With eBGP, the default behavior is that the next hop is of the advertising router, so the advertising router's IP address. But when we export those eBGP learned routes into iBGP, that next hop remains of that advertising router in eBGP, and thus we needed to configure R1 and R4 to have that next hop self, where they tell the other routers, if you want to get to this static route, if you want to get to this external network, use my next hop, use my IP address, because I know how to get there. I've got that eBGP connectivity. And of course we went through a few policy statements itself. This video had a lot of policy statements, but without them, that end-to-end connectivity from Enterprise A to Enterprise B, from ASN 65100 to ASN 65200 through service provider number 1, wouldn't have worked. So a lot of content, a lot of information. I really hope you found this video informative and useful. If you liked it, please give me a like, please give me a comment. I'm getting more and more interaction and I'm absolutely loving it. Let me know if you want me to create any content and I'll be happy to do so. Until then, thanks for watching. Stay tuned. Thank you very much.